what's like my own personal definition of universality that is helpful to me, which I think is only a slight spin on what is the usual definition, which is in the context of computers and minds. If you want to talk about universality, I think the sentence that you want to have in your mind has three parts. Universal system, or a claim about universality, is about, number one, a particular system, a computer, a brain, an alphabet, something that has a certain relationship to every member of some set. So A, you have a system, B, you have a relationship, and C, you have a set of things. And so if I make a statement which is of some form of universality, like, every language on earth has nouns. And you'd say nouns are a universal feature of human languages, you might say. And so this is a statement about universality. And if you were to break it out into these three pieces, you'd say, okay, the system here that we're talking about is actually going to be, I guess, nouns. And so nouns have a certain relationship to the set of all human languages. And that relationship is it's present in all those languages. And again, focusing on that set, it's a set of all existing or maybe historical human languages. It doesn't make a claim about anything outside that set, like an alien language or an animal language. It says, I'm defining these three pieces of this sentence. Nouns are contained in, and then lastly, all human languages. And you can imagine variants of this statement, which change any one of those variables. Change the nouns to verbs. Now you have a different type of statement. Change the relationship. You say, okay, it's not that, instead of saying nouns are present in all these languages, I could say nouns are essential in all these languages. Like you can't even make any sentence in any of them without this thing. Let's say that would be a different statement. It's not just part of the language that's common. It's essential to every single sentence in that language. That could be true or not, but that's a different type of relationship between nouns and these languages. And then lastly, you could tweak the set itself and say, actually, I'm going to make a statement not about all human languages. I'm going to make a statement about all possible languages, or all languages spoken in the antebellum South, or all dialects there, or something like that. And so that's the basic framing of, at least for my purposes, statements of universality. You have a system, a relationship, and a set. And so anytime somebody says, and often, by the way, when people talk about universality, especially in the context of language, they're making statements like that, like, here's a feature of language. I think it's relevant to or present in all of the languages you'll ever find. And one thing that's different between that kind of thinking and the kind of universality I'm interested in when I'm talking about the brain is that I'm not interested usually in a finite set of things that have existed. I'm usually interested in this infinite set of everything that could exist, which is it's a much bigger and more interesting set. So it's a more interesting type of universality, I would say. But ultimately, and just to add one more thing to that, and then we can kind of toss that around, is that a statement about universality, again, is about a system having a certain relationship to every member of some kind of set. Many things are true of only some members of a set. I know a lot of people. I don't know everybody on Earth. I know some people. And the some is the operative word there. And the alternative being all. I know all the people. So those are that distinction between some and all is the one that is most fundamental when thinking about universality. Because if you say I'm good at some things, or I could possibly do some things, that's not good enough for an AGI, for instance. I want a system which is capable of doing all things, literally all things. Maybe not right now, but it's capable of getting there. So there's some precision in terms of what that relationship is, what you're specifically trying to say. But anyway, zooming out here, the key points are statements of universality are about three things: a system, a relationship, and a set. And the fact that that system has this relationship for every member of that set. And lastly, some versus all is the key distinction to have in mind. But anyway, thoughts on that?
Can the set be arbitrarily big or small or whatever? Like, everybody in this room. So that is a universal statement. You have a relationship of knowing everyone in this room.
Yeah, and you can make the set whatever you want, although there are some sets are more interesting than others. So the set of everything that's on my desk is a pretty parochial thing that nobody cares about. A book written about that wouldn't be bought. But about the set of everything that is computable. Okay, now that's a set that's pretty interesting intrinsically, and that makes it valuable to a lot of people. And you could always gerrymander and invent your own arbitrary set. You'd say the set of all things, all languages on Earth, except English, and I'm going to make a statement about that. And you go like, well, that's kind of a little bit suspicious that you're, writing what you think is some book about something, and you're making one exception. You say actually, I think the more objectively important set is the set of all languages, not the set of all languages minus English. That seems a little arbitrary, to be honest. But in any case, that's a question again about the types of sets that are interesting. If somebody else came along and said, actually, the set of all languages except English is a legit set, and here's why, then fair enough. But the set can be anything. And one of the key distinctions among sets is whether it's finite or infinite. And I'm mostly interested in the infinite set of all the things that could be, though we can always make a set of finite things that are, that we can imagine or that currently exist or have existed.
Okay, but they are still universal statements, even without being infinite sets.
Yeah. And as far as I'm concerned, you're making a statement of the right form, and then somebody might look at that and say, actually, you're kind of bullshitting me. You're saying like, I know, I'm making a you could make a statement which is sort of a BS statement of universality. For instance, like, here's one, especially Zalalem, if you're looking at books on logic, I think they will sometimes use sentences like this where they'll say like, I have given $1 million to every person or every alien who has asked me for it. And of course, there's 0 of them. So you can say any statement about an empty set, and that So you'd say, oh, okay, well, in ordinary English usage and this commonsensical framing of it, that's not a good statement to make, though it's formally correct or whatever. So you have to distinguish between, on the one hand, statements that sort of fit this pattern of universality, and then there might be versions of it where you're like, oh, I don't care about that statement. That's a dumb statement. That's or whatever.
I was just wondering, so wait, am I audible?
Yeah.
Yes.
Okay. Is there something like, what is qualitatively different about the universal statements from the non-universal ones? Like, are they counterfactual in that they refer to, sounds like they refer to all possible things by some description rather than, I guess, not a finite set, but a known set. So like if we say all possible languages have this feature, that includes ones that we don't even know about. But so I don't know, is that
Yeah, I feel like you'd want to have some kind of generator of like classes. So to be universal, it applies to all things in this particular set that I have listed. Whereas you'd want something more like, I have some decision criteria that groups things, and all possible things that end up in that group, this rule applies to.
Yeah, you can define a set by enumerating things or have some more general criteria. And I think this falls under the broader heading of, when you're making a statement of this form, I guess what I'm really saying is like, I think of universal statements as statements of this form. And of course, any one of those statements could be BS or boring or false or whatever. But here's a format in which you could arrange universal statements. And so one of the ways in which it can prove to be boring is that it's a boring set or an arbitrary set or a small set. And you could say, I would be more interested in the set of all possible languages than in the set of languages some random dude happens to know. They're both sets, but one is more rich and intrinsically interesting.
I wonder, does a universal claim have to contain a description of what it refers to, but a non-universal claim does not?
So there's...
Or yeah,
Sorry,
as far as... I guess I'm just focusing on sentences of a certain form, and then you can have questions about how any of these pieces are defined, how you define a set. And at that point, that's a separate discussion, because my little format here just says, hey, I want sentences of the form things with relationships to every member of some set. How you define any one of those little pieces is up to you, and it could be valid or invalid. But just that 3-piece formula is sort of the focus here. Yeah.
There's
What
something
is-
special.
Oh,
Oh,
go
sorry,
ahead.
Bowen. There's something special about universal statements in that they can never be verified. They can only be falsified. And universal statements always entail existential statements. So if I say all languages contain whatever, then that means that any particular language will contain nouns. But I could always just say there is a language that contains nouns. So that's an existential statement, which can never be falsified because you can't go through all the languages to confirm. You can only verify it.
So that's only
You
true
verify it
for that's only true for infinite sets and things.
Yeah.
But if I say
Yes.
everything on my desk is edible, then I can test that statement and go through all of them.
Right. I'm using I'm using universal statement in a way that's slightly different from what you're saying, but similar in that the set is infinite. So the format of the universal statement, but infinite set.
Yeah. Exactly. Yeah. So I think for my purposes, then the interesting thing becomes saying, okay, within this little, really it's just a helpful device to just say, hey, these are 3 things worth focusing on: the system, the relationship, and the set. These are the 3 variables that are relevant to talk about. And so then the interesting questions all become about, okay, which system are we interested in? A particular animal, or all life forms, or the human brain. There's different things we could turn our attention to. A strand of DNA. What is its relationship to, all chemical reactions, let's say, or these kinds of questions. So you can turn your focus to many different things. And my main focus is on, minds. Okay, so minds have a certain relationship to, and then the question becomes, what set? The set of all possible physical transformations, building of rockets and planets and black holes, or everything that is computable. That's the most important one. What's that?
I was going to ask what you think the relationship between people is to the set of all possible explanations. So we have the system and we have the set, but what is the relation? Can synthesize or can create, I guess, but can we get more specific than that?
Yeah, and I think these are where the open questions are as well. Trying to get more precise about, okay, what are the relationships and which set? And so if we focus on the set of everything computable to start with, and then maybe we can dig into explanations, which I think are like a subset of that. Everything a computer can do, that'll be the set that we focus on. And then you can ask, okay, well, an AGI or a human mind should have what relationship to that set? And the 2 that come to mind for me as most important are, on the one hand, you should be able to create anything in that set, because that set contains valuable things. It contains relativity and instructions for how to build a rocket and all those things. So you want access to all that good stuff. So you want to have universal ability to reach anything in that set, produce it, come up with it, given that you haven't started off with it. So you have some building blocks that you have when you're born, let's say, and you are capable of reassembling them and building new blocks and whatever you need to do to come up with relativity and whatever else. So that's number 1. Number 2 is you want to be able to use anything that you've created in that set. Or to put it differently, maybe there's sort of 2 versions of this in my head. The other version is you want to be able to sort of navigate that set in any possible way. So I guess it's sort of a use anything in that set to move through that set.
Yeah.
So I guess the way that I maybe clear is to say that you want to be able to reach any point in that space, and you also want to be able to navigate and take any possible step in that space. And the reason for that is that, obviously if you can reach a point, that's good, but if it take you like 1 trillion years to do that, that's not so good. But if there's a shortcut where you can think at a higher level of abstraction, for instance, and reach that same endpoint in a decade, let's say Einstein thinking about what he's thinking about, he's reaching relativity in a way that some low-level computer program enumerating all possible programs is gonna have to take a few trillion years before it gets to that same result. So he's navigating the space using interesting ideas and getting to valuable places faster. So that's also important. Those are really the two fundamental things.
So isn't that reachability the same as tractability? I think we've talked about that before, but that's what's front of mind for me. I mean, does that not mean that getting to, any given program is tractable as opposed to the random number generator or something that's intractable? Is that not the defining line? Because I keep going back to that. But
there's a sharp distinction between what you can reach and how the resources required to do it. Because you can imagine navigating just a simple system like the number line. Imagine if you'd only move one step at a time. You could reach anything, any positive integer, but it could take you arbitrarily long. Whereas you would hope that, for instance, whatever number you have, let's say, have reached. So if you reach the number 10, that you could then like multiply your current position by that and then go to 100 in one step, and so on and so on. That would accelerate your traversal of the line. So you want something like that.
Yeah. So you could say for any possible natural number, if the machine can only add one, then it's intractable, perhaps, or something. It takes a very, very long time. But if the system has multiplication, then that could make it tractable. So now that makes that any possible natural number reachable. Would we say that, or do we mean something else by reachable, if not creatable in a not exponentially increasing time?
Well, the key question is the yes or no question of can you reach it, and ignoring the number of steps. You can reach any integer in a finite number of additions from 0. 1, 2, and there's no number you can't reach that way. So every positive integer is for sure reachable, as long as you don't smuggle in other assumptions like, the universe only gives you so much time to exist and do this the operation. If you ignore those physical constraints and just say in the abstract universe where we're doing this addition, you have infinite time and we don't care how long you take, then, simple additions of 1 will allow you to reach anywhere on the number line.
Right.
But of course, we care about the time it takes and the resources required. But that is a distinct, categorically separate question.
Mm-hmm. But isn't that like totally front and center to personhood? Because again, a random number generator could also reach quote unquote any number. So the whole point is we want to be able to do it efficiently, right?
I didn't say it wasn't important. I'm just saying it's a totally different question. So it's just useful to distinguish between them and know which one you're kind of addressing at a given point. Because, for instance, you could, to make the number line analogy a bit more computational and relevant to the mind, you'd say, okay, well, in a simple world, in a simple computational world, you could be Turing complete because you have, let's say, whatever 4 or 5 computational building blocks you need to assemble any program. But suppose that you were always stuck assembling new programs only by using those sort of atomic units. By the way, if you want to Google what I have in mind here, look for like combinators, those sort of interesting computational building blocks. Stephen Wolfram has some videos on that. And so if you have all the relevant ones, all the ones you need, a complete set, that's fine. But if you're stuck making new computations by gluing those together one by one, and you could never take other pre-built programs you have made and stick them together, those might have thousands of individual units in them, and you're taking a 1,000-unit program and another 10,000-unit program and making another one, combining those, or running one program and another, and making something really big. If you can't do that, if you're stuck just with this little, having little tweezers and making one little unit at a time, one computational atom, that's a very slow way to assemble new programs. And so it's going to be hard to reach a program if, let's say, you need a 1 trillion unit program. It's going to take you a long while to assemble that in this very reductionist type of way. Anyway, all that is to say that you could have a system which is Turing complete. It can reach anything, but only very slowly. You can have an alternative computational system that allows more recombination at higher levels of abstraction, which will allow you to explore the computational universe much more in much larger steps.
Interesting.
The whole question, it seems like to me, of AGI, or one of the central questions, is how to go from, like they call it in constructor theory, no design laws to something that can manufacture things beyond just the elementary undesigned primitives, like in the case of combinators. That's just yet another instance of this class of things. So that's, yeah, what I'm super interested is how does it get off the ground, basically? Once you have completeness, how do you go from primitive things that need no recipe because they're just the laws of physics, quote unquote, or the computational laws of physics in a mind? How do you get the stacking stable, ever expanding hierarchy of tools? And we know error correction is a big part of it, but I don't know.
Yeah. Well, one way to frame some of this is to say, like, the problem of intelligence is very similar to the problem of evolution and all these things, which you can sort of formulate as, if you start with a kind of a bucket of primitives, how do you get to more complicated things? And so if all that exists in the world are photons and protons and these kinds of subatomic particles, you could ask the question, how do you end up with atoms? Structure, a higher level structure, or molecules. And it could turn out that that's very easy. Once the universe cools down, these form pretty naturally. And so you'd have your explanation there. But then you'd say, okay, well, what about going from those units of molecules to a DNA strand? Because there are many possible variants of a DNA strand which are much poorer at storing information. But why does the one that works, well, why does that keep getting made and sticking around, as opposed to all these defective versions that could exist? That seems harder to explain. And ditto, you might say, for a brain, you'd say, okay, well, I can imagine a brain that has, it's like Turing complete, but how does it end up finding like good ideas? That seems like a different question. And so in all these cases, you're starting with this small set of primitives, or at least more primitive things, and asking how you branch out into this super, vast search space of combinations of all those primitives. So how do you reach out into that vast space and hit good stuff, given how unlikely that is? And that's the same question at each of these stages when you ask, how do you get these cool results from these more basic things?
Mm-hmm. I feel like I would want to have this relationship between humans and universality. I would want it to be something like a human can reliably error correct all possible explanations that can lead to progress. That's what I would want, though I don't think it's reliable. And
Well,
I don't think yeah.
Well, with a
Sorry,
lot
go
of
on.
these things, I'm usually trying to ask the question, if I can you roll something back? So that's maybe quite a high level thing that involves error correction and different things. And let me see if I can increase my volume here.
Yeah, you're a little quiet.
Let's see.
Maybe it's just me though. Is Carlos quiet for?
Oh yeah,
Quieter than the rest of it.
I have my Zoom set up to be high fidelity, original audio for musicians, it says.
Oh,
Nice.
Supposed to be a higher fidelity, but I guess it makes it quieter also. So we'll see what happens there. But in any case, whenever there's like a high level thing that you might consider, like the thing you were mentioning, Zachary, I always want to see if there's some simpler version that is the thing that matters. And maybe one version of this is talking about explanations. Like explanations, it's a little bit unclear what those are, but you can maybe back that up and say it's simpler to talk about the set of all possible programs. That seems like something we can really grab onto. We can talk about Turing machines. And then as to which of the programs, which of the things that a mind can do are explanations per se, maybe that's a fuzzy thing. Maybe we don't have to focus on that. Maybe, that's an open question. And likewise for things about error correction, that's more of a tool, I would suspect, than like maybe the thing to focus on. But I don't know.
Well, it's like the thing of, I can have um, a number, infinite number generator that just goes up in steps. It can answer any math problem because it can present every number, but it won't error correct to the correct answer, and that's kind of a major problem. And we would want to have people be able to actually settle on the correct answer for any problem that they're solving. So it's kind of the idea of similar to the infinite monkeys on typewriters with infinite time. Sure, they can produce anything, but of course, they won't be able to do it efficiently. They won't be able to error correct to it. They won't necessarily be able to use it in the way that you like to think of it, Carlos. They won't have the ability to navigate it in any coordinated way and all those types of things. So that's kind of what I'm thinking of with error correction there.
Yeah.
But of course, I think what I'm saying is very fuzzy and not complete. So that's just where I want it to be.
That is a good point, though. The random number generator cannot answer any specific question. It can't do anything specific. It can do anything, but
Right.
not specific thing. You can't choose what it will do. It has no function to it. I think that's
Yeah.
important. Yeah.
Yeah, the way that I frame this is that ultimately in all these discussions, there's only two or three real questions, and I think everything else is sort of a synonym of those or a combination of those. And the one of them that we raised earlier is about what you can reach. A system that can never reach relativity, well, full stop there. It's not a very powerful system. And then you say, okay, well, if it can reach it, can it do it efficiently? What kind of steps can it take? What kind of mutations can it make? That's a different kind of thing. And so again, if it was possible to reach it, but only in a trillion years, you'd say, that's not exactly what I'm looking for. I think what you're raising, Zachary, is something is a third issue, which is what if you have a system which can reach it? Not only can it do that, it can do it quickly. But then what if as soon as it hits it, it just says, forget it, and keeps on going?
Yeah.
Or it says, I've generated not only the correct version of relativity, but 10,000 others. And I think everybody, to be fair, we should just use all of those equally. So the next thing you do is not going to be particularly biased by the real one, the best one. So in that question, there are two things to address there. One of them is how do you recognize quality? How do you distinguish the good from the bad? And then the second version of that, or the second thing is, what do you then do about it? If a brain like blew up or something every time it hit a bad idea, that's not a very good system, let's say. And if you forgot things actually that were bad, that it might also not be ideal because maybe you want to remember that was bad and why it was bad and avoid similar bad things in the future. So there are different ways to handle, even once you assess that one thing is better than another, or one thing is very good, another thing is very bad, what you then do about it, how you exploit that assessment, then becomes the next question. But yeah, the first thing to ask is, suppose you have the right answer and you found it efficiently. How would you recognize it? Would you stop and think, I'm going to really exploit that good answer? That's what I'm going to talk about a lot. I'm going to remember that one. I'm going to invest in that. And all the other ones I'm going to invest in less. So that to me is what, I guess in my notes, I'd like to call that the problem of criteria. And you need an open-ended set of criteria because different kinds of problems, different types of opportunities require different sort of means of recognizing them. The way you recognize a good physics theory is not the same way you recognize a good ice cream flavor.
The criteria are just programs like all the rest. There's nothing special about them. I'm thinking you can't even reach relativity without error correction. So I don't think there would be such a system as one that creates thousands of theories of relativity starting from nothing. Because maybe there's no way to even do that tractably. You can only do it with, complete error correction or whatever.
Well, I think it's important to distinguish some of these questions, and this is kind of one of my interests is just trying to see where are there important distinctions where you can kind of address things separately. And so earlier I was saying you can address separately the questions of what you can reach with infinite resources versus what you can reach efficiently. And these are distinct questions. Not that one is less important than the other, but you can ask them somewhat separately, and that makes them easier to address. And likewise here, the question of what you can reach is quite separate from what you can recognize as good. Because I could have a system which is incapable of reaching anything, but I can give it these options and say, okay, you didn't find these options, but tell me which one of them is good. This is a separate task. And of course, the system we're interested in, the human mind and other things like that, or some powerful AGI, we want everything that we've discussed here wrapped up in that one system. So there is an integration that has to happen at some point and figure out how you do all these different things at once and make it work. But for now, you can sort of separate out those issues and say, okay, the problem of criteria is distinct from the problem of what you can reach, logically speaking, at least. Yeah, so you can have a random generator that comes up with relativity and a million other things, and I'm just I just have a bucket of computational primitives. I'm just keep shaking the bucket, you know. And if I keep shaking it long enough, a big relativity-shaped program will fall out of there, and that's fun. And then the question is, what do you do about it? And that's the bigger question.
So I want to go back to your initial the statements, the universal statements. They're including systems, relationships, and sets, and the ones that we're interested in are the infinite sets. Are there any constraints on the relationships that we care about? Like, I don't know something about an infinite set. So I have a relationship which is not knowing the thing about the infinite set. Now I imagine that's not interesting that is the case, and that's the universal statement. But it's matching the criteria that you've set so far for having an interesting universal statement. So what is it about the relationship that needs to be constrained to exclude that type of statement?
Oh, I would just say that within this sort of three-part formula of the system, the relationship, and the set, you can just have different things you're interested in, and there's no particular rule or anything. But yeah, I'm most interested in the set of all things that can be computed, maybe the set of all the physical things that can be made to happen. You can't. I want a system that can not only think anything but sort of do anything. Um, Both of those probably go hand to hand. You probably have to have both of those together, incidentally. um, but so that's once I've raised the point of, hey, these are the three parts of a statement about universality, then let's start talking about which ways you can fill each of those blanks
Yep.
in an interesting way. And as far as the relationships goes, those are what I've said earlier. Like, you want to be able to reach anything, you want to be able to use anything. Um, by the way, the distinction there is sort of like, imagine a workshop that could produce anything, but always could only use like very primitive woodworking tools. It could make a rocket, but it had to use like little wooden hammer and very primitive stuff. That's a worse workshop than one that can not only make anything, but that can make stuff and then use what it made. Like, I can make a new hammer and then use that hammer, and then can make a spaceship and then use the spaceship to go get new ores and then come back and use that stuff. Like, that's closing the loop and gets you to exponential progress. So you want to not only be able to have a system which can reach anything infinite set, but then also use anything in that set. And here's where things sort of open up for a lot of further thinking, because the idea of being able to use any program is a fairly abstract kind of statement, and actually it's sort of an umbrella statement, because there are different types of uses of an idea. One of them is to make more ideas. Another one is to use as criteria for assessing ideas. These are different uses. Another use would just be to like a mechanical use. Like, I have a addition program that can add two numbers, and you just apply that. I'm not maybe making any new ideas. I'm not assessing ideas. I'm just running this program. So it will be the further use of ideas. And so the question then becomes, which uses are important? And I think they're the ones I mentioned there. Creating new ideas, using ideas to assess other ideas. And the question for me is, I think those two uses are pretty clear. You want to have those, and you can ask what kind of mind can do that, what kind of system can do that. But then there's a further question of, like, is that all of them? Have I exhausted the list of all the requirements you need for an AGI? Are there any other senses of the word use, any other type of uses of the idea that matter? Anyway, so that's that. That's one set of questions.
Do you have conjectured answers to any of these? Like, what allows us? What's stopping us from? So we've established all the things we need. What's stopping us from coding it up? What are the immediate problems that you see?
Yeah, I think in each case, the question is, how do you achieve each one individually, and then how do you achieve them all together? Sometimes it's easy to state what you want and not so obvious how to get it. So in the case of like a Turing machine, let's say, you'd say, oh, I want something that can compute anything. And he's okay, well, what does that take? And the answer is in one sense quite simple, but is not obvious. And so I think that's true here as well, where you think, okay, well, I want a system which can use any idea that it makes. Okay, interesting. So let's say I've made an idea. What form does that take in a brain? This creation of a new idea. How is it stored or whatever? And is it the case that now that I've made this idea, depending on how it's stored, like maybe it is like you can imagine a world where it's like having a book in a library and it's, or it's at the bottom of some pile. Okay, well, technically it exists, but it's not really connected up right in order to be exploited and used and flexibly, connected to and this kind of thing. So you'd say, well, okay, that's the kind of system we don't want. We don't want a system that just like creates new ideas, but there are some like imagine a brain that could like produce new connections, but they or like imagine a brain maybe not that produced new connections, but it was unlike our brains. What it did is like made new neurons somewhere that weren't connected to anything. They were just like, okay, butted off like little cells. Say, okay, well, okay, this brain can make new ideas, man, and they're right there.
Yeah.
But you'd say it's not really, you can't use it anymore. It's not connected up right. Our brains seem to work differently than that. But what kind of connection matters? Like, I don't know.
Mm.
So the vague question there would be like, how do you produce new ideas in such a way that they are like pretty automatically or easily capable of being used by anything else? One thing I've sometimes thought about is that uh, any idea in your head you can kind of string together into a sentence. I can be like, I saw a dolphin with a tequila on the starship uh, shooting a gun at a black hole. Like these are, any of the concepts in my brain I can kind of shove together into a sentence. And that's an interesting property. How do we achieve that? Um, or maybe is that a trivial thing? Maybe some computer scientists would say, oh, like any memory can do that. Like you just have a key value pairs stored in the memory. And so you can just grab any one of them. So maybe the kind of mental architecture you need has key value pairs as a fairly primitive thing. Or maybe that's an overly, um, maybe that's a way of describing thing that's overly biased by how current computers work, and how, the way our minds work is actually quite different. Maybe you could squint at it and you could see some key value pairs, but really a neuroscientist would see a lot more. I don't know.
Mm.
I think another one of the relationships that's important is that you can group ideas or group programs, I guess, or relate the programs. As in, you can like compare rival theories, in a simple way of putting it, or say that these two theories are the same theory, or these two programs are somehow the same program, and you can know that they're the same program. Um, I'm not sure, Carlos, if that strikes you as fitting within one of your other things, like assessing, perhaps, or using in some unique way. But I think of it as a specialized function that's necessary.
Well, one thing I kind of left out is the idea of attention and like what you focus on as being relevant at the current moment. So like, yeah,
Mhm.
once you can create new ideas and once you can distinguish the good from the bad, let's say you can do these very well. That still doesn't tell you what you should be focusing on right now because, you're doing mathematics, but the lion is about to eat you. So a smarter person would recognize the lion and get out of its way and then think about the mathematics. So what is it about your brain that makes that happen? And maybe a more, another way of putting that would be to say, like, set aside the line example and just think of yourself actually just doing pure mathematics and saying, well, we have some mathematics that we know. There's a billion directions I could go on to try to think of some new mathematics that would be valuable. So, which of these branches should I strike out on? Because most of them, if I were to think about them, would get me nothing. And I could spend lifetimes doing that. So it actually matters, even if you're only interested in mathematics, that you can find good paths to go down. So what helps you do that? Um, and so this is what I like to call like mechanisms of attention. Um, and one of them it might be like novelty or surprise or interestingness. These are things which are fuzzily defined, but we have some sense of what they can be. Or logical conflict. You said a sentence, I said a sentence. They can't both logically be true. Whatever. And so that might be something to focus on. But that's only one thing that might focus you in some way. Uh, And so you might also say like anomaly detection. You know, I'm used to such and such happening, but I'm surprised by this thing. It's an anomaly in some sense, and that's where seeing levels of similarity might be of interest. Um, by the way, like the sense of similarity that you have, the concept of similarity is interesting because there are different forms of similarity, and something that I think is one interesting thing that the brain does is you can be in conversation and then say some anecdote that you haven't thought about in 20 years, and somehow it was similar enough to the present situation that you brought it up. But then as you say it, you might think, if you try to make explicit what was similar about it, it might be difficult or whatever, or maybe it's actually pretty easy. You'd say, oh, like you got fired because you said the wrong thing at this thing. And then I'd say, oh, that's like when I was in preschool and I got put in detention because I said the wrong thing. But say, these are all high level things. And one thing that's interesting about it is that somehow you experienced that thing in kindergarten and it was stored in your brain in such a way, despite not knowing what the future held or what things you would want to talk about or whatever needs there would be in the future. It was stored in such a way that that similarity could be detected, which is kind of weird. That's an interesting property because it's like it's almost like saying like imagine you have to arrange a library today and keep it sort of formed properly, such that in 100 years that arrangement will be useful, despite not knowing anything about the future. You might say. But maybe you know enough to say, these concepts will be relevant and whatever. So just in terms of how you store information and retrieve it, that's already a pretty interesting thing. But core to that is what you think of as similar, what definitions of similarity you have.
Do you think similar things? I mean, yeah, it's not just similarity, though. I mean, my thought has been that if you have like a big graph, the whole system is a graph of programs, and then as a new one is made and is successful, then it is just put near where, or it's sort of local to where it was made. I mean, there's some like spatial aspect. And so next time when, when activity is happening in that region, then all the other programs that were useful before are first to be activated. But then you're assuming there's some sort of like, pulse moving around type situation, which seems like a big leap. But I mean, that is what is roughly talked about when they talk about the human brain, different pulses moving around and causing cascades and criticality and all that stuff. So that's where my head goes when we talk about how the programs are stored and stuff like that.
But the question is that a necessary thing, or is that just happenstance for how the mind, like how the human brain is organized currently?
Yeah.
It could be that you.
Yep. Go ahead.
I would say it could be that you could arrange them in arbitrarily different ways and arbitrarily more efficient ways or worse ways and so on.
Yeah, the sorting is just an efficiency thing. But the question is it necessary for some reason to have everything connected, which is that's all a graph is really. Everything present is connected. If it's not connected, it's not part of the graph. So maybe there's something kind of fundamental about graphs that, like you're saying, Carlos, that way the system would never just make something but then isolate it so that it's not usable. Everything is always connected, and things are still decaying and being revitalized, perhaps. But I don't know. It seems like it needs to be connected.
I second Carlos's intuition that, like, I think the connection between sort of the ideas is crucial and really important to the whole of it, instead of like, I think it's more a discovery than it is an efficiency problem. So like the way you connect the graphs and the way you connect the dots. Does that make sense?
Yeah. It's not really efficiency. It's its own thing that's like performance.
Yeah.
Not what we're
interested. Yep.
One side note that I think is interesting sometimes is to think of my own personal notes, which form a graph, as a sort of model of the mind, and to wonder what the similarities and differences might be. Because, as I work with notes, you might say part of that is specific to note taking and individual productivity. But then you might say, well, actually, there's a convergence between the needs of that situation and the needs of any knowledge management situation, including the brain. And you might say, actually, I'm finding that it's very helpful to think not only in terms of like previous generations of note-taking tools, which are more hierarchical and like folders, documents and folders, documents in a hierarchy, one single outline. Every book is a sequence of pages, and that can contain a lot of good stuff. But you might say, actually, that's an inferior way of arranging information compared to a graph, because a graph can do that and also much more. And so there are just intrinsic advantages to working with graphs as opposed to outlines and hierarchies. And so you say, okay, well, that proves to be true for note-taking tools and for the brain and for friend networks or databases in various contexts, and it's for the same reason. And so in the case of my own notes, you have a document with some contents, with a name, and other documents can refer to that name, and that's useful. And the body of the document, the note, can refer to other notes. And so there's a high level similarity there in terms of this associative kind of framework of named things, maybe to how the brain works. It's at least an interesting thing to compare and contrast. Brains and note-taking tools.
Yeah.
Graphs.
I'm kind of going back on the efficiency idea again now as you were saying that. I'm thinking, what we're talking about seems like a person is something that can go from one point in the space of ideas to another, right? Of its own, by its own light, as the saying goes. So maybe it is actually you need I think we've talked about this before, but there's I picture like a combinatorial escape velocity concept where maybe you do need several different types of efficiency to come together in one system, sort of like all hands on deck, because that's the only way to get from like one program to another that is meaningfully different at all, because the space of possibilities is just too dense, no matter what the implementation of the system is. So maybe it is a matter of efficiency, and you need enough sources of efficiency, or it just doesn't happen. There's too many combinations to explore. So I don't know. I'm still.
I think I would argue. I think it would be more like problem situation than it is because I think once you understand the from where you are, where you're trying to go to, from the current problem you have into where you like to be, for things that I don't know, and I'm sure a lot of people don't know, the mind just creates the idea and you just connect it almost very rapidly. Once you understand, it's like whenever you're programming something, understanding the problem is almost as sometimes you're pretty much all you got to do now is just type out the solution. Now that's not always true, but I think a problem situation is more more the guiding thing when connecting ideas than sort of random combinations.
Yeah, there's a question of how you go down, if given the many possible paths you can go down, which ones you should go down.
Yeah.
But in this issue of the architecture of the brain and the fact that a network might have advantages over some more strict hierarchical system, let's say. I think one of the things you have to ask here is, and this is true of the broader question of how should you design a brain, or how should a brain be made? I think the first question to ask is, what is its fundamental purpose? What should it be good at? And then how do you make it good at those things? And if you're a programmer working on some database, let's say, one of the first things you'll have to ask is, what does this thing need to be good at? Does it need to be good at reading? Does it need to be able to support 1 million users or 1 billion users that each want their data very quickly? Because if you want to do that, that requires a certain architecture that's quite different from a system that says, actually, I want to make a database that's very good for one person to come in and analyze and summarize all the data for that day, or all the data of this company over the last 10 years. Those are different operations. One of those, you want to be able to pick a small piece of data and deliver it to a user very quickly and do that for lots of users. The other one, you want to like summarize lots of data. And that could literally be the difference of like, I want to have data that is indexed by user or data that is indexed by time or something else. And those are going to be radically different things and inefficient for one purpose and efficient for another. And so for the human brain, you might say, like, oh, I want it to be able to add a new idea and efficiently be connected to all the relevant things. I just want to be able to drop it in and say, oh, I had this new idea. And because of the way I generated it, I sort of made it out of, let's say, 3 components. And imagine that you have a network with 3 nodes in it, already pre-connected. Your notion of a table is already richly connected to your worldview. And so imagine that you grab that, and then you grab this other thing, which says computer. Put these into a new sentence. My computer is on the table. And you've formed this new thing, but it's already connected to everything else that you know. You've just sort of drawn a new little line around these 2 concepts which already are richly connected. And so now you have, for free, basically, very cheaply, created something new, but also made use of everything old. And that's quite a nice feature to have. And it isn't one that, you can imagine alternative ways of doing things that wouldn't have that property, maybe. So you say, okay, that's cool. I want that property in my thinking system. I don't want to have to recompute the relationships between everything every time I have a new idea. I could do that. I could make a system that would do that, and maybe it would work, but it would just be much more costly, and every time. Yeah. So I don't want that. So that question you want to ask again and again and again, and say, what should this thing be good at? What is its core bread and butter as a computational system? And it isn't, for instance, doing things that we usually, like computers do, like run through and add numbers and do that, 1 trillion times in a row without error. We could do that, but it would be very, it's not what we're good at.
Yeah. So again, I mean, I can't not picture a graph the entire time you're saying that. Basically, what we have is a system that has programs connected throughout a graph, and then something like a regulatory network in genetics is what I've been thinking about. Is something sort of the composition is happening by activating different regions of those graph or connecting different regions and then trying many different connections, because composition of 2 programs is one feeding into another. Or so yeah, it seems like it's all about connections and trying connections, and then the ones that solve a problem in some sense are reinforced, something like that. So that's what I'm thinking.
There's a kind of a cool idea from the world of Clojure, which is a Lisp programming language. And in that language, they said, we want to have, we have various reasons where we want this property of when you create a new variable, like it can never change. And we think, okay, we want this thing in our system. But then to implement it actually required a very inefficient copying of a lot of data. So basically they said, we want to have a programming language. We think this would be better if it had this feature. But actually that feature is very costly. At least if you think about a naive way to approach it. And then somebody else came along and said, oh, actually you can get this thing that you want very cheaply. And what this amounted to was saying that if you have some data in your system, previously with this naive thing, you were going to have to copy all the data you had before and make a new copy of it. And this way you could do operations on both separately. And whatever you do on the new thing won't affect the old thing. And that's nice. It's kind of like saying, I want to make a new version of a song, so I'll just copy it over and I'll leave the old song alone and I can always go back to it. I don't have to write over it. So that's a nice feature to have. So, but they said you have to copy the whole thing. If it's 10 gigs, you have to copy 10 gigs every time you want to make a change to it in order to make sure the old one is safe. So they said, actually, you can do a structural sharing thing where you arrange the system in such a way that you can keep clear all the things you're doing that are new to it. So you can basically say, it's almost like having like a sheet of paper. And instead of like retyping the whole thing, you just add a little sticky note to one part of it. And a sticky note, you can see the new thing. Everything you wrote, you can see everything you wrote before, and you can have the sticky note on top of the new part with its new writing. And you can lift up the sticky note and see what's underneath. So you can just make the edit, and it's efficient. And so they did something like that. And I think of that as being an interesting case of saying, okay, well, now let's think about that in the context of the brain. You want to be able to do something efficient, and you want this feature of like every time I make a new idea, it's connected to everything else. And I can imagine a naive way of doing that where you like recompute everything, but that doesn't seem very good. But so is there a way of achieving this thing that I want, but doing it elegantly and efficiently, with a little bit of cleverness? Like once you know what you want, maybe there's a way to get it. And in the end, it may not be that complicated, but it does achieve this very important thing in a very efficient way, and that makes all the difference.
Mm. Yeah. Mm.
But yeah, so I think just to reiterate the stuff about universality here and see if anybody else has any other questions. The overall picture was that if you're interested in universality, you want to focus on three things: the system, the set of, or yeah, you're usually going to be making statements about this system has this relationship to every member of this set. And then you can talk about different systems, different relationships, different sets. And those sets could be finite or infinite. The relationship could be, such and such contains this thing, or can represent this thing, or can reach this thing, or can use this thing. All kinds of relationships are possible. And the systems you might be interested in are genes or minds or computers or whatever. It's pretty, I think, a rich framework that I think the main goal of it is just to say that you want to focus on those things. And I don't think there's anything else that has to be considered. I don't think it's missing anything, this little three-part framework. And I think you do have to address each of those three parts to understand fully what you're talking about. So I think it's just like a helpful little framing for the discussion. One other thing I'd say, by the way, is that in the context of AGI, I think I mentioned this a little bit last week. It's one of the core things that I think is unique about this sort of Popper Deutsch flavored approach to AGI, because usually people are interested in performance of a system and improving that performance according to some benchmark. But that's somewhat different from saying, hey, I think that there's just a way of not like taking a system, making improvements, and just continuing to improve it, and increasing some performance number. But to say like, oh, this system can do anything. Like, it just has crossed some kind of binary, qualitative boundary. I think that tends not to be what people are thinking about mostly. They're thinking more about, hey, we got this performance. I want to increase that number, increase the accuracy, increase the speed, increase this. That's quite a different thing. Imagine if you'd done that with like Turing machines. You'd say, I have a computer and it can compute more and more and more, versus, I have a computer that can compute anything and I can prove it. By the way, just to, this is something that I think is always interesting when talking about like universality and Turing machines and stuff. They are surprisingly disappointing in a way because they contain like no information about how to do anything, a universal Turing machine. All it is like a system for like taking in an input and copying it over and simulating what the real machine would do. So the universal machine is actually in some ways the most boring one. It can't do anything that's useful on its own. All it can do is wait for you to tell it the recipe, and then it can follow it. So in that sense, it's the worst Turing machine. And if you had tried to make a more powerful computers, you would have said, okay, I have a computer here that can do some things. The way to improve its power is to make it be able to do more things. So I'm going to take Turing machine A, Turing machine B, and I'm going to make a new Turing machine A plus B. And it has a little toggle switch, lets you do the A program or the B program. So now it's better than either machine on its own. So you say, okay, cool. Turing machine A plus B is more powerful than A or B separately. And then you just keep on doing that. A, B, C, A plus B plus D plus C. So you're like adding more and more programs into it. But this is exactly the opposite path to go down to reach universality, which says actually the best program is the best machine contains no programs. It doesn't contain A, B, or C or anything. All it does is listen for you to give it A, B, C. That's kind of a wild inversion. And it turns out that's the actual machine that we want. And that's the one that gets built and conquers the world.
Yeah. So the analog is that a person is a program that actually consists of no programs, but it can make all possible programs. because the person, the part of us that's the person, does not have, isn't the knowledge, right? It isn't the programs, it's program creation thing, like the crest of the wave, as I think of it. Because knowledge, all the programs and explanations and knowledge we've already made, that could be run by any computer in principle, unconsciously. So yeah, there is kind of a parallel there, right? The person, like the Turing machine, has no programs to run. It is the runner. The person has no, I guess, is not running any program other than program creating program. Maybe there's
Kind of. I think you can kind of think of this as like built-in versus learned or created, and I'm saying it in a somewhat revelatory way, but I think it's common to everybody interested in machine learning, where they say, "What if we made a system that instead of building in a bunch of stuff, it figures it all out on its own?" And so that was true of AlphaGo, for instance, where they say, "Oh, we're going to build in knowledge of these games," and then later on, they I think made AlphaStar or a different program that said, "Actually, we're going to delete all the knowledge of human games and have it figure it out how to be humans still, but without building anything into it." So this built-in versus learned is king, and I think everybody is interested in the algorithms, which you just say, "Hey, it's a very simple algorithm, but now we're going to let it run," and therefore everything that we hope all the valuable things we care about, it can discover. They don't have to be built in from the start. So that's true in general. But anyway, I think what is different is that people tend to be looking for some sort of performance that is not about this qualitative distinction between non-universal and universal.
Yeah.
Though some people do. And then, so I think one thing that's interesting last week that I talked about was that I see like this flavor of research that I'm interested in as like having three pillars. One of them starts with Popperian sort of evolutionary problem solving. Second is to take universality seriously. And third is to focus on explanations, explanatory knowledge versus non-explanatory knowledge. And in each case, you sort of are taking a view that is a little bit different from the mainstream. And so if you focus on this universality piece, there is actually, most of the mainstream doesn't take that seriously, I guess. But there are people who do take it seriously. For instance, AIXI. This is a Bayesian approach to saying, hey, I'm interested in a set of all programs and a system which could somehow exploit that set. However, they approach it from an empiricist direction as opposed to this Popperian evolutionary direction. And so they end up taking kind of what I would expect to be like a wrong turn. So you have to get all three pieces right, I suspect. The Popperian side versus the empiricist side, the universality versus saying just like, oh, increase performance in some numerical way. And then lastly, looking at explanatory knowledge as being quite special. But anywho, yeah.
I gotta hop off to make some lunch, so maybe I'll stop and join.
Well, cool. Now, because you're a universal mind, you are capable of doing this despite the fact you were born unable to. So
Yes.
that's as good as an illustration of any as universality.
I synthesized the lunch making program only recently.
Nice. Well, cool.
All right. See you
Well,
guys
we can
later.
end it there. Adios, everybody. Thanks for joining.